Hello YouTube, welcome to my channel. I have been working recently on a procedural terrain generator in Unreal Engine 5 using a marching cubes algorithm that works dynamically at runtime using the new dynamic mesh actor. So I want to showcase that today, go over a little bit of the code and release it to all of you guys to use for free. So without further ado, let's get into it. You can see my world here. We just have an ocean. We have our little starting submarine, as well as a couple fish I've placed here really for testing purposes more than anything else. But you can see when we start, after a short hitch, we are in our game world, and we can actually dive in to see what the terrain is looking like here. So as you can see, we have fully runtime generated terrain with foliage, in this case just grass, on it, as well as some collectible item actors. Now excuse me for directly ripping Subnautica, but you have to start somewhere with prototype design. And as you can see, this is fully 3D. So we have cave functionality, and let's equip our oxygen tank before we run out of oxygen there, and pop back up to the surface, catch our breath, and we'll go back down. So all of this is calculated at runtime, and has collision enabled and works seamlessly with PCG, with a couple of slight caveats that I'll get into. But yeah, it really is a very impressive system for how early days it is, and I was quite impressed with the performance. Now, I will say that this case that I'm working with has a lot of constraints that make this particularly possible. So if we go here and we do stat FPS, you can see that we're running around 40 FPS, and really that is GPU situation. But you can see our slight hitches down to like 29 as we're moving quickly in one direction. You can also see some pop in there. That is actually adjustable. I can calculate these chunks further off, and we won't have that pop in, but we might have more frame rate considerations. But again, we'll get into all of that later on. I just wanted to show you what this actually looks like in runtime, with just kind of this simple terrain function that I whipped up. The plugin has three main processes: creating a scalar field with noise generation, converting that scalar field into triangles and vertices using the marching cube algorithm, and then finally creating the terrain at runtime using Unreal's native dynamic mesh actor. The scalar field is the main point of modification, allowing for many types of worlds by using a combination of deterministic rules and seed-generated noise. The key concept to understand is that everything above zero, or the ISO level, is air, and everything below it is land. The marching cube algorithm samples the scalar field at each corner of each voxel and calculates the triangles necessary to build the isolevel surface. Finally, we pass the triangle data to dynamic mesh actors to build the mesh async on compute meshes and then append at runtime. Jumping into the code, our terrain manager class holds the config variables for the marching cube algorithm. These include the voxels per axis and the voxel size in centimeters. Together, these adjust the marching cube resolution. The isolevel adjusts our land-air bias, letting us create cavernous or cramped structures. The chunk class allows you to extend the functionality of the actor class, for instance, adding custom PCG. Spawn distance and despawn distance are self-explanatory and control the extent of the active terrain. And finally, update interval is a custom tick for the system to save performance. Next, in our marching cube class, we initialize different noise functions. These use the free framework fast noise light, which will be linked in the description. For the example provided, we use 3 different noise generators and set the octaves, lacunarity, gain, and frequency for each. The Fast Noise to Noise tool is a great free resource for visualizing different configurations quickly. The final piece of code we'll look at is the most important, and how we build the actual terrain. The val variable represents whether the sampled point is solid or empty, depending on if it is below or above the ISO level, respectively. First, we define a circular world of world radius that increases with depth as we approach the edge. The height at any given point is calculated as seafloor average. Once we have the seafloor average, we lerp between our main noise function, which represents caves, and 1 representing empty space, based on the seafloor level. We then bias values within 1 meter of the seafloor to have more land, creating smaller openings for the cave system and more terrain for us to spawn grass on. Finally, we calculate the maximum depth of our tunnel system and lerp between our noise and solid ground using the same method as the top. This is just a simple algorithm to create a basic underwater biome, but more complex logic can be used to create multiple biomes that blend together or place bespoke points of interest within the random generation. The repo is available for free to download on my GitHub with instructions to install.